All right, so it's about time. Then let's start class. Can you all hear me? Okay, thank you. So today is about the force system resultant. Last time on the previous class, we have learned that the force that act on the rigid body produce the force and also produce a moment. So the moments, we can find the direction by using our right hand, right? The right hand rule. By placing our palm, 4 fingers on the plan that contain force vector, the force vector F and then the position vector R. Therefore, the moment that produced, of course, is will perpendicular to both vectors, both R and both F. So you can see that it's not direct along any axis. So, okay, but sometimes we need to determine the moment of the force about specified axis. For example, from these figures, so you can see that we exert the force to this rand on this direction. And we can find the moment by using point O as a rotation point and a position vector that direct from point O to the line of action of F. So the moment will perpendicular to these two vectors, which is this vector MO equal to R cross F. But the thing is, in your real life situation, your moment can only rotate about this nut, right? Because the nut cannot rotate along this axis. It must be direct along the y-axis. Here the problem, because the moment that is really produced is not on this axis. So we have to change this moment and make it into my, from mo to my. We call this moment or force about a specified axis. Okay, so we need to find the moment about y-axis. So how can we do that? We can just resolve this MO into its component. Okay, so for these figures, MO is located along the XY plane. X and Y. Okay, and we have MO. So we can resolve this MO into its component on My and Mx with one angle, theta. So the component My along the y-axis is the projection of Mo on the y-axis, right? So it can be found by using the dot product. Normally, we have Mo equal to R cos F. So we want to move this force Mo into the y-axis. So we have to dot with the direction of y to make it become the moment along this axis. Okay, so R cos F, we have scalar. No, we have vector. The result is a vector. And we dot this vector with the unit vector again. Okay, so the formula is the moment about any axis equal to the unit vector of that axis dot with the resultant moment that produced from that force. It can also be rewritten in the form of metric by this equation. Instead of I, J, K on the top row, we replace it with the component of unit vector UAX, UAY, and UAC. And here we have the moment about any axis, but just a scalar, right? Because all the number in this matrix are scalar. Therefore, the results become scalar. So these results show the magnitude of MA, only the magnitude. The scalar can be both positive or negative, which indicate the direction of MA along the A-axis. So with just one scalar define the magnitude. Then we have to make this scalar become a vector by using the dot product again. Then from this equation, you need to dot with UA again. And finally, you will have the moment about any axis in the form of Cartesian, MAX, XI, MAYJ, and MACK. By using dot product two times, right? The first times find the magnitude, and second times make it into the Cartesian form. And from this dot product, if it is positive, then the direction of MA is the same as UA. But if it is negative, then the direction of MA will become opposite to UA. Okay, so let's see one example. This question wants you to determine the moment about this lot MA. By the force F, we tend to rotate a lot about AB axis. From this lot, we exert force at point C and use, you can either use A or B as rotation point. Okay, you can find MA or MB. We all know that the moment about any axis, in this term, it is MA, MAB. That must be the moment that produced by the force MF. Okay, so for this M, it depends on the rotation point MO. And then dot with a unit vector along AB. For the dot product, we know that it has the property to switch its place. So MO dot UA or UAB dot MO have the equal results. So first thing, we need to determine the unit vector of AB. Let's suppose that UAB direct out of point A. Okay, so this direction is up to you. You can also assume that UA direct on opposite direction as well. Okay, so let's find UAB. From this point, what do we know? Okay, we know that point A is located at origin point. And what about point B? We have to find the coordinate, right, which is 0.4, 0.2, and 0. Then we can use these two coordinates to find position vector R. Okay, so from point A to point B, we have 1 R, RAB. Okay, so first thing we know RAB. That is equal to the coordinate at the ending point minus the coordinate at starting point. So RAB equal to 0.4I plus 0.2J. K is 0, so we just have I and J. And from this position vector, we can find the unit vector AB. That is equal to vector RAB and divide with the magnitude of RAB. Okay, so how can we find the magnitude? Do you remember from the second class? We can use sine law. RAB equal to the square of all component with the square root. Okay, so replace this term and this term on this equation, and you have the unit vector UAB. Okay, I already find UAB that is equal to 0.894, 0.447J. Okay, so we already have UAB. Next, we have to find MO. So for this MO, you can decide that you want to use point A as a rotation point or point B as a rotation point. Because if you change the rotation point, the position vector will be different. For example, if you choose A, okay, if you choose A as a rotation point, point O, you can use the position vector AC or AX like this. Because the force direct along this direction, each position vector has intersect with the line of this action. Or you can also use other vectors like this or like this. As long as you have all information that you have, like coordinate. Okay, so or in case that you choose the point B as rotation point, you also have RBC or RBX, right? Like I explained the last time, either position vector that you choose, you got the same results. So choose the one that easiest. So for me on this time, I will choose A, D. Because it's direct along the x-axis. So I have only one component in direction of I. Then for me, M O equal to R A D cos F. Where RAD equal to 0.6 I. And cos with F. On this problem, the F is giving as a magnitude, but you can see that it's direct along the direction of C in negative axis. So we know that F equal to minus 300K. Okay, so we have moment, we have the unit vector, we have everything that we want. So let's put it into the metric form. MAB equal to UAB dot with MO. In the metric form, the first row shows the component of U. Okay, the second row shows the position vector R. And the last row, the force F. And from this metric, you will have a scalar that defines the magnitude of MAB. Okay, and from this magnitude, you have to make it into a vector by dot with UAB again. Okay, so I will give you the results. You can review and redo this question again by yourself. So finally, we have MAB in Cartesian vector form as 72I and 36J. At first, if we use the right-hand rule to find the moment, we will have the moment that direct along the y-axis, MO. But after we dot with UAB, then the moment become MAB on this direction. Because the magnitude that you can find from this metric is positive. Therefore, the direction is direct along the first UAB that you define. And how it's rotated, you can use the right-hand rule. So your thumb will point along this MAB or this axis, and the curve of your forefinger show how it's rotated. So it will rotate counterclockwise along the lot AB. Okay, why we have to learn to find the moment about any axis? Like the example I show you in the first place, because on the real life situation, you cannot rotate the moment along this axis, right, MO, because this nut can just only rotate about its point, that is y-axis. So sometimes you have to change from the moment that you can find into the moment along any axis.
I have one question.
Yes.
Doesn't I cross K equal to J?
On this question?
Yeah. The
this part?
RAD cross. Yeah. That.
Yes, you can. You can use this metric form or just call it by using the formula like AB sine theta like that. You can use that too.
So it will result in like J form?
Yes.
Okay, thank you.
Okay, so that's the first topic, how to find the moment about any specified axis. Next, let's see the couple of a moment. I think you are familiar with this word because you have studied since high school, right? Let's see it again. What is couple? So in case that there are two forces having the same magnitude, parallel to each other, but it's act on the opposite direction, or it is negative to each other. We call these two forces as a couple, where the resultant force of the couple equal to 0, because we have F equal to F on one direction and another act on the opposite direction. So it is equal to minus F. Then the result equal to 0. So the result from the couple is just a couple moment. For example, on this steering wheel, we exert two forces from both hands with equal magnitude. So one will pull down while other one will push up. Because the resultant force equal to 0, therefore only one movement is just rotation, but we don't have any translation. Okay, and of course, a rotation or a tendency of rotation is will act on one specified direction. Okay, like this steering wheel of a car. The moment that is produced by this couple force, we call it a couple moment. In the coplanar system, the magnitude of this couple moment can be found by using this equation, m equal to fd. Normally, we can find the moment that also equal to fd, but the d will be different. For normal moment, d will measure from the rotation point to perpendicular and intersect with the force. But for the couple moment, d become the distance between these two forces. Okay, the same d, but different definition. You can also find the couple moment, the dilation of couple moment by using the right hand rule. Or it's obvious, right? Because if you can use the dilation of F to help you find the dilation of the moment. So for this system, the moment will rotate in counterclockwise, which is mean positive. Okay, the point is distance D is must direct from one force to another force and also perpendicular to both forces. However, in 3D system, it is difficult to determine the perpendicular distance between the couple, right? Because you have to differ with x, y, z axis, which quite difficult to measure the direction. So we use the position vector to define the distance. Let's see this system. Suppose we have a couple F and minus F in this space. Then we use point O as rotation point. So from point O to the force F, we have one position vector RB. And from point O to the force minus F, we have one position vector RA. The result moment about point O on this system, that is the moment about point O equal to RB cos F at with RA cos minus F. So we have the same force vector F. We can take them out into one force F. So we can rewrite this equation again as RB minus RA in the bracket and close with the force F. So how can we find the results of RA minus RB? Let's see this triangle construction. Okay, suppose that the resultant of, okay, so let's see from this triangle construction. RB is same like the result vector from RA plus R, right, by using the head to tail method. So let's switch its place and make it as unit vector R, the position vector R. So it is equal to RB minus RA. Then we can replace this equation into this equation. And finally, we have position vector R cos the force vector F. Okay, as shown in this square. So why do I have to prove this equation to you? Because I want you to observe that the couple moment that's produced from both forces, F and minus F, is depend on the position vector R, that is the distance between these two forces. But it's not related to the point O anymore. It means that the couple moment of this force become a free vector. Okay, it is a free vector because it's not fixed with this point. At first, it is fixed because we use the position vector from O to the line of action of each force. But after we change it into the couple moment, it will depend on the direction between these two forces, not the point O. That's why it's become a free vector. So it is a free vector. It means that we can move the couple moment anywhere on the space. Okay, for example, we have this space x, y, z, and have one couple moment mc. We can move this couple moment anywhere on space while it maintains its magnitude and direction. Its unit vector must be the same. Okay, you can move from point O to point A to point B. It is still the same moment. Okay, so this how the free vector means. You can move it anywhere on the space, but maintain the magnitude and direction. Okay, so what is equivalent of the Hopper moment? So let's consider these two figures. If F, from the first figure, if F equal to 30 Newtons and F dash on the second figures equal to 40 Newton. In case that we want to produce the same moment, the same amount of moment, what happens if the force and the direction is different? So in the first figure, the couple moment equal to Fd, right, which is 30 and the distance 0.4. Also, we have 12 Newton meter of moment. While on the second figures, the M equal to Fd. So the F changed to 40 Newton and the directions, the distance become 0.3. This system also produced the couple moment equal to 12 Newton meters. So you can see that these two systems, the couple moment of these two couple are equal, but you can see that the distance between the couple, if it is become closer, you need to exert a greater force to rotate this wheel. So this application is this of this fundamental. For example, the steering wheels on vehicle. So let's compare the steering wheel between a car and a truck. So if you compare these two systems, you can see that when you want to turn a truck, you need to exert the larger couple moment, right? The one method that you can save your energy is that make the steering wheel become bigger. So the distance becomes greater and you can exert the force, the minimum force. Okay, so that's why the size of steering wheel in the truck is larger than in the car. Okay, we have to increase the distance in order to decrease the force. Since the couple moments are vectors, so we can determine the resultant by vector addition. Like in this system, we have two couple moments, M1 and M2, acting on different lots. So we can find the resultant moment mr by add these two vectors together. So it's act on the different lot. How can we add them directly? Because we said that the couple moments are free vector. So we can use, we can move this m1 into this point, and then move another vector to share the same rotation point. Okay, after we move this to couple moment and make it share the same point, then we can add it directly. Okay, so that's why we have mr equal to m1 plus m2. Or we can write it in form of sigma, mr equal to sigma r cos f. Okay, let's see one example of a couple moment. They want you to replace these two couple acting on the pipe by resultant couple moment. Okay, so you have to find mr equal to m1 plus m2. Okay, 5 minutes. Please solve this question. All right, so how much is M1? M1 is the moment that produced with this couple, A and B. So you can see that if you use the right-hand rule, the couple moment of AB will dilate along the x-axis. So it has only one component equal to 6di. And what about M2? So you can find the magnitude of M2 by using M equal to Fd and then resolve this magnitude into the x, y, z axis or into Cartesian form, or use make the force C or the force D into Cartesian vector and cross with D, that you also have to shade it into the Cartesian vector and then get the cross product. So for M2, the position vector must be DC and cross with the force FC. I use FC because it's direct along the positive direction. Okay, so if you use the right-hand rule, you can see that the moment is perpendicular to Fn RCD on this direction. And also this couple moment perpendicular with x. So we have only two components on y and x. That I have M2 equal to 20.5 J and 30K.
Wait, so you like multiply like 125 with 0.3 and then you turn it into the yx component?
Yes, you can do that. Or you can first change the force into Cartesian form and then change this 0.3 into Cartesian form and cross product.
I see.
Either method is okay.
So we have to cross like both I and j at the same time?
Yes.
Oh, and then like plus it together. Okay. Okay, thank you.
Okay, so these two forces, M1 and M2, you can see that it uses the different rotation point, but the couple moment is a free vector, right? So we can move. Okay, let's move it into origin point, M1 and M2. The point is you can sum the couple moment or any moment just in one case that the line of action of the moment must be intersect to each other. Or you can say that all moments must share the rotation point. Then you can add. Okay, so we can, if it is a free vector, we can move them. But I will show you later if it's not. How can we do that? Okay, so in this problem, move M1 and M2 and let it share the same rotation point. Then we have MR equal to the summation of all couple moment. Okay, so add all terms together. Okay, so you can see that if we have the couple moment, it's quite easy to calculate, right? Because we can move and make it share the same point. So we will use the couple moment and apply it to the application, how to solve the problem. That one is called simplification of a force and a couple system. So in the system that we have, many forces act on a different point or the axis and cause the effect of translation and rotating on the body. Okay, so let's suppose that we have one lot, one state lot, and we hold on other end. Let's say point A and B. We hold this stick at point B. And next, let's exert the force along this axis on this direction, the force F. Okay, now we want to move the force F from point A to point B. So at point A, we have force F. So let's insert a couple at point B on the same line of action. Insert F and minus F. After insert this couple force, it will not affect the system, right? Because the resultant on this point equal to 0. So the summation FR still equal to force F. Okay, so what's next? You can see that this force minus F and this force F can cancel each other. Okay, let's say this pair can cancel each other. Then finally, we have only one force F left on at point B. So from the first step, the force located at point A, and finally, the force become located at point B. The condition is that point A and B must stay on the same line of action. Okay, so now we can move the force from point A to point B without modifying any effect on the stick. And this also proves the property of transmissibility of the sliding vector, that the vector can slide along its line of action from one point to another point. So we can say that a vector can slide to any position if they still share the same line of action. So it's easy to move a force. So let's see another system. We still have the same lot and holding this lot at point B. But this time, the force acts perpendicular to the lot. Again, we want to move the force from point A to point B. Then let's insert a couple. F and minus F. The resultant force at point B equal to 0, right? Then it's not affect to the overall system. Now what happened? This pair of force, F and minus F, you can see that these two forces are a couple. And a couple force will produce a couple moments. Then finally, on this system, we have one force at point B, force F. And these two couple will become a couple moment. And this couple moment can move to anywhere. So let's move this couple moment to point B.
Professor, didn't each other canceling out?
No, it's not cancel because it's not on the same line of action.
Oh yeah.
Okay, so we have force F and one couple moment, MC. And this MC equal to force F multiple with direction D. So you can see that we can change the form from the first type into the final form. And here is called the equivalent system. Okay, if you move the force on the same line of action, you can move it directly. But if you move a force from one point to another point, that these two forces is not act on the same line of action, it will produce one couple moment, okay?
So basically, if you put the same force on the same point or
Yes.
action line, it's going to cancel each other out, correct?
Yeah.
Okay, thank you.
Okay, so we can use this method of equivalent system to move the forces to any point on the space. For example, on this figure, if we want to use the point O as the reference or the rotation point, the force F1, okay, can be moved to point O, but it must produce one couple moment F1. And next, we will move the force F2 to point O. And this must be produced one couple moment MF2. For these two couple moments, we can move it to point O directly. So we have this equivalent system where the force F1 and F2 start at the origin point O. Okay, and then we can find the resultant system where sigma FR, the resultant force, equal to sigma F, and MRO, the resultant moment, equal to all couple moment on this system. Okay, and here how we use the equivalent system to move all forces and help us solve the problem. So let's try one example. So this question wants you to replace this system by an equivalent resultant force and couple moment acting on its base at point O. Okay, two force is given, F1 and F2. Okay, and one couple moment, M, equal to 500 Newton meter. So this M is a couple moment. Okay, so 5 minutes. Let's see what you can do. All right, how was it? It's not that difficult, right? Okay, so we have two forces, F1 and F2. That's giving us the magnitude of the force. So we have to change this force, F1 and F2, into Cartesian form or vector form. For F1, it's quite easy because it's direct along the z-axis. So we have only one component in direction of minus k. And for F2, you know the magnitude equal to 300. But what about its direction? Okay, the angle is not given, right? But you can see that from point C to point B, you have the coordinate. Then you can change F2 into the vector by the dot product, dot with the direction of UBC or UCB. To find the UCB, you have position vector from point C to point B. So we have RCB equal to minus 0.115 I, because it's on the direction of minus x. Distance of the y-axis equal to 0.1 j. And from this, you can find the magnitude of RCB equal to the sum of all square with the square root. And then replace these two terms to find the UCB. And then dot with the magnitude of the force, 300. And finally, we have F2 equal to this term. Now the force F1 and F2 is used point C. They are used point C as a rotation point. But this question wants you to find the moment that acting at the point O. So we have to use the equivalent system to move the force from point C and B into point O. Okay, by moving the force, it will produce a couple moment. Let's see the force F1. Okay, we have the couple moment M1 from the force F1. Okay, but the thing is, this force is direct to the rotating point, or it intersect with this point. Therefore, they don't have it doesn't have any couple moment that's produced equal to 0. Okay, because the line of action of this force intersect with the rotation point.
So we can say that at point O the radius is 0, so F1 is 0.
Yes, we can say that too.
Okay, thank you.
For the couple moment M2, of course, we have to find by using the cross product. The position vector direct from point O to point B, that is, intersect with the line of action of F2, and cross with the force F2. Okay, so from this equation, we have the proper moment M2 in Cartesian form. Okay, we already moved the force F1 and F2 to point O. Now this couple moment, because this question said that the moment M is already a couple moment, so we can move this moment directly from this point to this point. And next, let's change this magnitude form into a vector form. The angle is given, so you can just resolve this couple moment M into each axis. Or if we just rewrite this structure, okay, it's act along, it's act on the CY plane. With one angle, theta. So you can resolve this couple moment into MC and MY. By using this triangle. So after resolve, we have M in Cartesian form as this. So now all the force and all the moment has located on the origin point O. Right, we have M with the force F2, the force F1, and the couple moment that's produced by these two forces. And M1 equal to 0. So now we can find the resultant force, Fr, and also the resultant moment, Mr. Here for the force, we have only two forces, F1 and F2. And moment, we have M and M2. Okay, so here are the resultant force and resultant moment of the point O or this space. Okay, so here this example show you how to use how to apply the equivalent system to help you solve the problem.
Professor, may I see the calculations for moment 2 again? How do you get that? I'm confused. For
Which one?
moment number 2.
Moment M2.
Yeah.
Okay, so the step to get the moment M2, we put the equivalent system of force F2 at point O. F and minus F. And these two forces produce a couple. Okay, so the couple M2 equal to F R cos F. R is the position vector that defines the distance between these two forces. Okay, so RB. So this system produces a couple moment. Okay.
So RB is like negative 0.15 I plus 0.1 J.
Which one? Which one again?
RB. Yeah.
All right. Direct from point O to this coordinate.
Yeah. I see. Okay.
And then we just do the cross product.
Yes. By using metric or using this form, the cost directly.
Wait, you can multiply like that?
Yes.
Okay.
Like I cos J become K like that.
Okay.
So the J component of F2 is positive 166.4, right?
Yeah.
But in the next page on the next page here it's like negative 166.4. The FR one. Yeah.
Oh, it should be negative. Okay, sorry. Oh, here it's already negative.
So
Right, it's already negative.
okay, thank you.
Why do I got a different answer? With different moment?
Really?
Well, basically the same number, but different symbol.
Maybe when you shoot the force F2. So for the force F2, did you get this equation?
Yeah. I do.
Oh, like how is positive become negative, right?
I mean, the entire M2 has a different symbol, like from both negative become both positive. And I wonder, what did I do wrong?
So if you write it in the metric form, okay, you have this form.
Oh,
and
wait.
be careful when you draw it.
Oh, wait. I think I got
It's
it.
down. It's become
I
negative.
select the wrong order. I put F first, then R. Oh.
The R must be the second low. Okay.
I'm sorry.
It's okay.
Well, I think I'm pretty much clear and through. Thank you, Professor.
Okay. Okay, so the couple moment is one application to help you find the equivalent system. Another system is called reductant of a range. So normally in three-dimensional system, the resultant force and the resultant moment are not perpendicular to one another. Therefore, it cannot be reduced to an equivalent system directly. But we can resolve this MR. Here, for example, this FR produce MR, this MR. And this MR also resolved into its component, which is M parallel and M perpendicular to any axis. So you can see from this construction, this form. So let's plate it into coplanar system. So we have C and A axis. And this MRO located on this space. This MRO can resolve into their axis. Okay, if we use C as reference, we have MRO parallel. And another axis is MRO perpendicular. Like resolve into two components on the perpendicular axis. So what is the purpose of this reduction? Okay, how can the first system become the second system? Okay, from this moment M perpendicular, we can resolve or replace this moment by using a couple moment. It's like if we move this force Fr to another point on the B axis. Okay, let's say from the first page. Okay, if we move Fr to this point, we have to insert a couple Fr and minus Fr. And this pair of force produce a couple moment. Okay, and this couple moment act along this direction. Okay, not this direction, on the opposite direction. Right, use right hand rule. This force Fr will rotate clockwise direction. Then it means that the moment is negative. And the moment is perpendicular to the force F and distance D. So it's act on this direction, M, C. This MC is a couple moment that is a free vector. So we can use this MC and make it locate at point O. We can move and make it locate at point O. So what happened? You can see that these two moments can cancel each other. That is M perpendicular and this MC that produce from this couple moment will cancel each other. And then it's like we move this force F from the point O to any point P. And because M perpendicular has cancelled with the couple moment produced by the force moving, then we have only M parallel left. And this M parallel also a couple moment. So let's move it and share the same origin point with FR that you have the third system. So you can see that for this system, the movement is translation and also the rotation. Okay, on the same axis. So let's suppose that the line of action is axis C. The moment will rotate about this axis, and also the movement will translate along this axis as well. We call this movement as a wrench or a screw, right? When you are turning a screw, it will both rotate and also translate along a line. Okay, so here are another equivalent system, a wrench. Okay, if you're confused, you can ask me. I can explain again. It's like the method to get rid of one component of this couple moment. Okay, so let's apply into this question. This question asks you to replace the force system by an equivalent dissolved force, and also application of a pedestal. So you can see that all forces that act on this system act parallel to the z-axis. Okay, so this want you to replace all resultant force into one point. Okay, so first thing that you can do is to find the resultant force. If equal to FA plus FB plus FC. Okay, and by moving all forces to point O, all forces will produce their own couple moment. So MRO equal to MA plus MB plus MC. Okay, and from this couple moment, resolve it into MR parallel and MR perpendicular. Okay, next step is want you to get rid of this term. Okay, so to get rid of this component and also MRO, and it will left only the FR on the system. This question wants you to find the location or the coordinate x, y, z. That after you move the FR to any point on the space, the moment will delete, will all replace. Okay, so here your task. And for today homework, one question. Also replace the force F by the equivalent force and couple moment at point C. Okay, for this question, try to solve by yourself first, and I will send the answer to you later. Okay, sorry because we run out of time, so I cannot explain in detail. But I will send the answer to you.
Both homework and this exercise?
Homework only one question. But this one just try to review the class, and I will send the answer to you. You don't have to submit.
Okay, thank you.
Okay, so for today's class, do you have another question? Or why are you doing your homework or review your class? If you have any questions, you can ask me again.
Where do you put your record? The recording of this meeting? Yeah.
I will send it to you on the live group.
Oh, line group. Okay.
Yes.
Line group. Wait, we have a line group? You mean the engineering mechanical line group or the
Third generation group.
third gen?
Oh, I can send you by using Canvas too.
Oh, on Canvas. Okay.
Yeah.
So if you can send it on Canva, that would be appreciated.
Okay.
Yeah, thank you.
If in case if you still don't know, she already posted her Google Drive in RI third generation group.
Or
Yeah.
Google Drive.
So
Okay.
don't forget to check it out, or I'll send it to you later.
Okay, thank you.
Okay, you have another class on 10:30, right? So I let you make a race and prepare for the next class. Okay, so thank you for today and see you tomorrow.
Thank you, Professor.
See you tomorrow.
Yeah, see you. Have a nice day.
You too.
Goodbye.